Okay, we're talking about how they classify D and L sugars based on how they rotate plain polarized light. And then eventually that moved into a more general classification. Again, D-glyceraldehyde does rotate light to the right and L-glyceraldehyde to the left, but that's not true for all sugars. Now, there is one other interesting sugar that this D and L does match up with, and that is D-glucose. D-glucose does rotate light to the right. And in fact, D-glucose is known in medical settings as dextrose, meaning the sugar that rotates light to the right. And L-glucose would be to the left. But that's not true for all sugars anymore. So that's the historical context of where DNL comes from. But what you need to know is that DNL refers to this chiral atom furthest from the highest oxidized group. So when we draw it in the Fisher projection, we come down. That is the chiral center furthest from the top. Notice that the OH is off to the right, and so that's classified as a D sugar. It has a specific name, allose, that we'll talk in a second, but we would generically classify this as a D. It is a aldose sugar, and it has 1, 2, 3, 4, 5, 6. So it's a D-aldohex, and since it's a sugar, it would add on the ose. So D-aldohexose. And notice that glucose is also generically classified as a D-aldohexose. And of course, this would be classified as an L-aldohexose and that as an L-aldohexose. And I just can't stress this enough. Remember that there's no relationship between dextrorotatory and D sugars. D and L, this little d and the little l tell which direction it rotates plain polarized light. That has to be determined experimentally. R and S that we talked about before and D and L are actually structural features. So if we look at the structures, we can determine if it's a D or L or an R or S. So again, over here, we can see how it's determined. Just a chirality center furthest from the C double bond O. So if it's off to the right, it's a D sugar. Off to the left, it's an L sugar. So we have a whole class of these aldoses. And so we have the simplest sugar. This would be the D-aldotriose, and there's only one of those. If we add another carbon in there and we get tetroses, for the D cases, we only have two. Notice that this center right here is constant. The very last one is off to the right. So this is the D family tree. And we have one more center of chirality, and notice we have both options right there. Well, if we extend one more carbon, notice the very last center is all D, and then at the other two centers of chirality, we have all other possibilities. And again, if we go down to this bottom one, these are the D-aldohexoses. The very last center is the same. And then the other three, we have all possible combinations. And so we have three centers. And so there's two possibilities there. So 3 squared, 2 cubed, two possibilities, 3 sites equals 2 times 2 times 2, which is 8. So there's 8 possible D sugars, D-aldohexoses specifically. Now there's a whole nother family, the L family tree, but those aren't found in nature. So we are more concerned with the D sugars. Now some of these we should know. We won't have you memorize them all, but you should know the structure of D-glucose. Let's pick another one, D-galactose. So those are the 2D aldohexoses that you should know. Okay, now there are some ketoses. So if you notice, the simplest ketose up here has no chiral center because the ketone's right in the middle. So this is classified as a sugar. We actually break down sugars into this dihydroxyacetone in glycolysis in our body. But the first one that actually gets a center of chirality is actually the D-ketohexose there. And the reason for that is we're using up one of these chiral centers with our C double bond O. So we're going to have fewer chiral centers in ketoses. And so again, we have several examples of these. You can see again, we keep the last position constant, and then we have both possibilities here with the other OH to the right or to the left. And then down here we have the D-ketohexoses. Again, we keep the very last one constant because these are all D sugars. And then we have all other possibilities here. So we've got 2 chiral centers. It can be in 2 possible positions. So we're going to have 4 possible D-ketohexoses. And we should know a couple of these. And so the ones that we should know would be fructose. That is a really good one to know. Okay, so for right now, what we should know is, oh, and I forgot one on the previous page. Sorry about that. There's 4 that we need to know. Ribose, we need to know ribose. If you've ever heard of DNA deoxyribose nucleic acids or RNA ribose nucleic acids, that is a biologically important sugar. So we've got 4 that you should be able to draw their structures of: D-ribose, D-glucose, D-galactose, and D-fructose. So really only 1 ketose sugar. So those you should be able to draw out. Now the structures biologically, they aren't just linear. They actually tend to fold up into a ring. And that's what we'll talk about in the next lecture. Just to prep you for it, we actually have an alcohol and we have a carbonyl. Alcohols and carbonyls can react together to form hemiacetals. So you may want to go back and review the hemiacetals in the ketone aldehyde chapter because we're going to form lots of hemiacetals and acetals here. And I'll show you that mechanism in a second. And when these fold up into rings, they can fold up into a 5-membered ring or a 6-membered ring. Now, they don't have double bonds in them, but the names that we use are based off of these 5- and 6-membered rings known as furan and pyran. So if you fold up into a 5-membered ring, you're referred to as a furan, and then ose because you're sugar. So a 5-membered ring is a furan. And if you fold up into a 6-membered ring, you are a pyran ose. Again, ose for sugar. And notice that we have a hemiacetal. We've got this common carbon right here that is sharing 2 oxygens. So we've got the oxygen here that shares a bond with that carbon, and oxygen here. And that is going to be a very special carbon that we need to be able to identify. That is what's referred to as the anomeric carbon. And that is where the carbonyl previously was. So right here, that carbon right there is referred to as the anomeric carbon. Very important carbon for carbohydrate chemistry. And again, in its previous life, it was the carbonyl that was involved in making the hemiacetal. So we'll follow up on that in the next lecture. Talk to you then.